Welcome to the next video in measure theory and probability. This is video 3.1 on product sigma fields. By the way, when a video has some decimal point like that, that just means that I thought of making this video somewhat after the fact. I had skipped talking about product sigma fields, but after developing a bunch of other, videos further along, I kind of decided I needed to come back and insert this in between videos 3 and 4, so that's all that means. And this corresponds to part 1, chapter 1, section 1 of the textbook. Now, if you have some two sigma fields, we'll call them E1A1, right? That's the first measurable space. So A1 is the sigma field there. So when I say that something is a measurable space, I just mean that it's set together with a sigma field. That's just what a measurable space is. And then I have a second one, E2A2. A natural way of putting together the sets, E1 and E2, is to take the Cartesian product. The question is, what is then the natural way to put a sigma field on this new set? And this is answered down below. Let's first of all define the set of all Cartesian products for any two measurable sets taken from A1 and A2. So that's what this capital Pi is. It's the set of all Cartesian products. Then the product sigma field is the sigma field that is generated by pi. Right? So pi by itself is typically not a sigma field, so we need to sort of generate a sigma field from it. The notation for this is a circle with a times in it, right? So it's not the Cartesian product. The O times indicates that it's related to the Cartesian product, but a little more complicated. Now, just to give a little bit of discussion about sort of why I'm doing some of the things that I'm doing, as I've read the textbook, it has become clearer and clearer that the book is not going to use the sigma field on the real numbers that I'm used to. In the measure theory that I've studied up to this point, the sigma fields that are typically used on the real numbers is the Lebesgue measurable sets, which is often denoted with a script M. However, the textbook uses the Borel sigma fields. So what's the difference? Well, the Borel sigma field is a proper subset of the Lebesgue measurable sets. So in some sense, when we ask what's the difference, a difference between them is that when you use the Lebesgue measurable sets, this means you get to measure more sets. So the Lebesgue measurable set sounds better, right? Well, on the other hand, the Borel sets actually have just about everything you need in practice. Although there are some sets that are Lebesgue measurable but not Borel, they're very hard to find. You wouldn't know they're missing if you didn't have them. Moreover, the Lebesgue measurable sets are very hard to construct, and once you have them, they are complicated objects, and so using them in proofs often makes proofs kind of tricky and complicated. Now, I debated whether I should switch from this book to one that uses Lebesgue measurable sets, and maybe I would return to this book when I was ready to start talking about probability theory. And the reason why I thought maybe it was worth switching textbooks is because although M does seem like it's more trouble than it's worth, it might still just kind of be a disservice to the student to not know anything about it, right? I mean, if this is an important object in the field of measure theory and we never introduce it and talk about it, then maybe that's just kind of a disservice. So I was wondering if I should switch to a different textbook. I often have this bad habit of getting started in a project and then realizing some part of it that I don't love and then switching to some other project. So I was in a little bit of danger of doing that again. But ultimately, I decided to stick with this textbook and to just not even bother talking about the Lebesgue measurable sets. And the reason why I made that decision is because I get a sense from having looked at a few other textbooks in measure theory that mathematicians today don't really seem to care that much about the Lebesgue measurable sets, and they're happy to simply work with the Borel sets because of their improved simplicity. Also, by the way, the Borel measurable sets have the advantage that they kind of generalize to any given topology, and so a lot of what we do and say about the Borel sets here for the real numbers carries over to other topologies. So, maybe it's kind of a nice, sort of more unified way of doing things. So anyway, that kind of convinced me that by skipping the Lebesgue measurable sets, we're perhaps not losing that much, right? And not even in the sense of skipping over things that the field of measure theory thinks is important, right? Like we're not even missing something that mathematicians think is important, so maybe it's fine to just skip it. So that's why I'm continuing on, and we're not really going to talk about Lebesgue measurable sets.